Fellowship and an Einstein Fellowship before moving to the University of Washington. Matt did a lot of seminal work in my field of 21 centimeter cosmology, which is where I got to know his name. But today he's going to tell you about, I always hate it when the introducer reads your title for you, so I'll let you take it away, but the title's up there, and very happy to welcome Matt McQuinn.
Yeah, thank you so much, Johnny. It's a total pleasure to be here. Yeah, I'm going to talk about something that is a bit out there. I think the physics is super cool. So, hopefully that's another motivation for sitting through this talk. If you have questions during the talk, I love questions during the talk. I'll try to paraphrase for the YouTube if I remember, but please feel free. So the starting place for this talk is this famous Edwin Hubble 1929 diagram that essentially launched cosmology as a field. This diagram wasn't made too long after we actually realized that there were other galaxies in the universe. And so what is plotted is on the y-axis is the velocity of galaxies that were measured by people in the decade before Hubble made this plot. And it had been known that almost all galaxies are moving away from us. So every point on this plot is a galaxy. And then on the x-axis is distance. This is 1 million parsecs. A parsec is 3 light years. 1 million parsecs we're going to call a megaparsec in this talk. A megaparsec is like a nearby galaxy. These galaxies are not very far away. And so Hubble had access to the largest telescope in the world at the time, at Mount Wilson in the LA area, and so was able to measure distances to galaxies further away further away than others, and make this diagram. And Hubble's primary way for measuring distance was that there's this pulsating type of star. It's a pretty bright star called a Cepheid. That if you measure its pulsation period, then you know its luminosity. So there's a relationship between its pulsation period and its luminosity. Luminosity is the same thing as power. So how much power is emitted? If you know how much power is emitted by an object, then you measure the flux on a detector, and that's all you need to measure the distance. So that's how distance is measured in this diagram. And so Hubble boldly then took these points and drew a line through them, and he said that velocity is proportional to distance with some proportionality constant that we now call the Hubble constant. And we could just read off what that constant is in this diagram. So this is 500 kilometers per second. And this is a million parsecs or a megaparsec. So the slope of this line is 500 kilometers per second per megaparsec. And so the measurement of that slope has a tumultuous history. So Hubble's measurement, we now know, was way high, off by an order of magnitude. He made a ton of mistakes. And gradually over time, the community realized and corrected those mistakes. And then by the 1980s and 1990s, the uncertainty in this parameter was of order a factor of 2. There was actually a camp that claimed it was 50 kilometers per second and per megaparsec, and another camp that claimed it was 100 kilometers per second per megaparsec. They were, of course, enemies. In the 90s, there was another innovation, which we realized that there was this type of exploding star called a Type 1a supernova, which could be as bright as a galaxy itself, where we thought we could also figure out what its luminosity is, that it had a standard luminosity. And actually, our method for calibrating that luminosity was then to find supernova in the same galaxies as these Cepheids. And we knew the luminosity of the Cepheid, so we could then calibrate the luminosity of the supernova. And this process of calibrating things using methods that we've calibrated at shorter distances is called the distance ladder. Okay. And so as time proceeded, the errors on this parameter decreased. And we reach the present day where our direct measurements using these Cepheid-calibrated supernova there are claims of 1% errors. That's the blue points. However, we have other methods now for inferring this constant. And these other methods disagree, some of them at the 10% level, like, for example, the cosmic microwave background measurements. And this tension, and they also have 1% errors. And so this tension between the direct methods and these other methods is referred to as the Hubble tension. And this is a somewhat old diagram, but that just illustrates this tension. And so in the middle, what's labeled late are these more direct methods. This shoes is the Cepheid calibrated supernova, which gives us the smallest errors currently of the late probes. And then the early are using the cosmic microwave background, which I may have just called CMB a second ago. That's cosmic microwave background, or analogous methods that are sensitive to early universe physics. These are a bit less direct in that the way we infer the Hubble constant is we take our model our very successful model for cosmology, which is called the lambda CDM model. Lambda stands for vacuum energy, CDM cold dark matter. So we take this model, it has 6 parameters. One of the parameters is the Hubble constant, and we fit this model to the anisotropies in the CMB, and out pops the measurements of these parameters, including the Hubble constant. And this comes out to be low relative to these late probes. And this could be because there's a problem with the model. The model might be making some assumption that's not true. Things, for example, things might be more complicated. Or it could be that there's some systematic that's leading to this discrepancy. We just don't know. And in particular, people have shown that if it is a problem with the model, it has to be that we have to invoke new physics when the universe is a few 100,000 years old, which is the time that the cosmic microwave background is coming to us from. Any questions or comments? Okay. All right, so are we stuck? How are we going to make progress on this issue? So maybe we find a systematic, and maybe the most likely place is in the Cepheid calibrated supernova step, which leads to the smallest late time errors. But if that's not the case, we don't have a lot of ideas for how to really advance these measurements. And so our best idea is to use neutron-star mergers with the next generation of ground-based gravitational wave detectors. And so the idea there is similar to the methods I've described, where if you have 2 neutron stars that are merging, we think that we can infer the luminosity and gravitational waves that come off those neutron stars. And if we're also able to figure out what galaxy they're in, to figure out their velocity, then we can put them on a Hubble diagram. And the idea is with these neutron star mergers, it's mostly clean gravitational wave physics, and so maybe this is a cleaner probe than these Cepheids and supernova. However, a big issue with these neutron star mergers is we really don't have great predictions for how many that we should discover with the next generation of gravitational wave detectors. We think we got lucky. There was one event that LIGO detected, but it's unclear how many we will be able to get in the future. So today I'm going to discuss a totally different possibility for measuring this Hubble constant. It has the advantage that it's totally geometric. It doesn't rely on calibrating the luminosity or knowing the luminosity of that's emitted by various astronomical objects. It has the potential to scale up to much higher precisions, as we'll see. It potentially can measure the expansion history and not just H0. That's what we're going to talk about on the next slide. And it can potentially do other interesting science aside from cosmic expansion, which is something that I'm going to just briefly address at the end of this talk. Okay, so in the first slide, I showed you velocity, which is the y-axis here, versus distance from Hubble's 1929 measurement. And remember that distance was going out just a few megaparsecs. This is a gigaparsec. A gigaparsec is 1,000 megaparsecs. And so if you go out much further than a megaparsec, how the velocity of objects changes as a function of distance is no longer a line, and it depends on the geometry of the universe and the different energy constituents in the universe. And so when we measured this relationship in 1998, what we found is that the shape of the measurements in this diagram was consistent with the universe having some mysterious negative pressure substance that we call dark energy. And you can kind of see this in this plot, which is this magenta curve, which says flat dark energy model. That's our favored cosmological model, and that goes through the points. But we want to measure this better, and in fact, there's a lot of uncertainty currently in how dark energy is evolving. We want to test whether the dark energy is a cosmological constant. And there are even some recent indications that maybe it's evolving, but they're very, very low significance. Okay, so that's the background, and now we're going to ask the question, are distance measurements via parallax to extragalactic sources possible? If you don't know what parallax is, that's going to be defined on the next slide. Okay, you may know that our best way of measuring, or our most robust way of measuring distance in astronomy is called annual parallax. And the idea for annual parallax is very simple. We're going around the sun, we're looking at astronomical objects as we go around the sun from different directions. And so sometimes an astronomical object, when we're looking at it from this side of the sun, it's going to appear juxtaposed on background stars, that more distant stars, in a different place than when we're on the other side of the sun. And so we can use that to measure the distance to that object using extremely simple trigonometry, where this is 1 AU. We measure the angle that it changes on the sky, which is called the parallax angle, and this is a right triangle, so we can solve for the distance. And so we're now going to, and we've been able to do this, do parallax measurements out to 10 kiloparsecs. In fact, this has been revolutionized in the last decade with the Gaia satellite. Actually, before that, we were really only measuring parallax out to 100 parsecs before Gaia. For cosmology, unfortunately, we want to go way further. We want to measure the parallax to distant galaxies. And in fact, it turns out that in order to make distance measurements that are interesting for the expansion of the universe, you want to measure parallaxes to greater than 100 megaparsecs. Because less than 100 megaparsecs, it turns out that different structures in the universe are pulling on other structures, and this causes them to have velocities that depart from this linear relationship, which we call the Hubble flow. And so you really need to go to see galaxies that are further than 100 megaparsecs to really be probing the expansion of the universe with the precision that we need. Okay, so what would it take to measure parallax to galaxies that are further than 100 megaparsecs away? And for this whole talk, we're going to take our fiducial distance as 200 megaparsecs. It turns out that 200 megaparsecs is the median distance of supernova measurements of the Hubble constant. So if I have a galaxy at 200 megaparsecs, then again I just do this trigonometric calculation, and the parallax angle that I have to measure is in order to detect its movement on the sky as I go around the sun. I have to be able to measure 5,000ths of a microarcsecond. That's a super small angle. This turns out to be 10,000 times smaller than the parallax angles that Gaia is able to measure. It's 1,000 times smaller than the parallax angles that were measured with the Event Horizon Telescope that took these images of black holes. Okay, so what would it take to resolve a parallax angle of 5,000ths of a microarcsecond? Well, this is also a really easy calculation. The angular resolution of a telescope is the wavelength divided by the size of the telescope divided by the signal-noise ratio. The signal-noise ratio, if that's higher, I'm able to centroid the image of my astronomical object better. And so for because of the direction this talk is going, we're going to assume a wavelength of 5 centimeters, which is a radio wavelength, to evaluate this. I'm going to assume a relatively low signal-to-noise ratio, which is a signal-to-noise ratio of 10, also motivated by future things you're going to see in this talk. And so if I do that, then this sets the size of the telescope. And so the size of my telescope needs to be an astronomical unit for this angle to be roughly the same as this angle. And so in order to be able to detect this parallax angle, I need an AU-sized telescope. You might say, what the heck is an AU-sized telescope? Of course, we can't fill in a dish that's an AU in size. And so, but here we're talking about the radio. And so what an AU means in the case of a radio is you can break up, it could just be 2 dishes. It could be, and a baseline. So if I have 2 dishes that are separated by an astronomical unit, 2 radio dishes, then I can get this angular resolution. Of course, we want to measure this angle with an error of 1%, and so we're going to need even larger than an AU, and so that's the direction that this talk is going. And so we're going to eventually imagine missions where we have radio dishes that are in the outskirts of the solar system, and that are trying to detect to measure parallax angles that are very small. But before we get there, we're going to go in all sorts of directions. And so there are going to be, I think, 5 digressions where we're going to just elaborate on certain physics that we're going to hopefully combine in the end, and then have an epiphany. Okay, so first digression is global satellite navigation systems. So we're all very familiar. We have our phone. It tells me to order a meter where I am on Earth. How does it do that? Well, there are these satellites in mid-Earth orbit that are transmitting some electromagnetic signal. They have some carrier wave that's of order 1.5 gigahertz, and on top of that carrier wave, there's some code where they modulate the electromagnetic waveform, and every satellite has a different code. And your phone knows what the code for every satellite looks like, and so it's searching for these different templates. And when it locks on, it knows the distance to the satellite because it knows when this code was transmitted. Your phone has to lock on to 4 satellites because it has 4 space-time coordinates that it needs to calibrate in order to know its position. If your phone had an atomic clock, it would only need 3 satellites. But the clock on your phone, unfortunately, isn't that good. It turns out that this technique scales up really well. If I have 2 radio dishes, and I point them at each other, and I separate them by 30 astronomical units. Remember, 1 astronomical unit is the Earth-Sun distance. So 30 astronomical units is like the distance between Earth and Pluto. If these dishes are 8 meters in size and they broadcast of order a 30-watt signal, then they can measure the distance between each other to about 1 centimeter in a minute. That's amazing. And this is going to be important. Okay, that was first digression. Second digression is quite related. So I mentioned really long baselines. When you have a really long baseline, and we call this very long, and you're correlating electromagnetic signals, we call this very long baseline interferometry. Very long baseline interferometry, in a sense, is similar to global satellite navigation systems. But rather than a satellite, you have some astronomical source. In this image, it's a quasar. And so that quasar has some electromagnetic signal that hits a dish on Earth, and then at a later time than this dish on Earth. However, the template, the waveform is the same that arrives at this dish as this dish. And so you can, if you align the waveform that arrives at this dish with this dish, then you can measure this delay, this tau. And it turns out that you can measure this tau to 1 over the bandwidth of your instrument divided by the signal-to-noise ratio. So if your bandwidth is like a gigahertz, then we're talking about sub-nanosecond timing. So you're able to measure the distance, this extra delay to a fraction of a nanosecond. And this has actually been done to great effect. In fact, often these dishes are these dishes can be separated by continents. Like this could be in North America, and then this could be in Europe. And we've been able to measure these baseline links so precisely that we can see 1/10 of a millimeter changes per year, which is actually 10 times smaller than the motion of tectonic plates. And so we can watch how these dishes are moving around owing to continental drift. Okay, this is a question for you guys. What is the longest baseline where we've actually been able to do this, to correlate the voltages, do VLBI? Is it 0.2 Earth radii, 1 Earth radii, 3 Earth radii, or 50 Earth radii? Who thinks A? B? Okay, a lot more. Not many A's. 3 Earth radii. C. Anyone think D? Okay, some people think D. Okay, some people know the answer. The answer is D. So there was this Russian satellite, 10-meter dish, called Radio Astron, that orbited out to the moon. And it was correlated with big dishes on Earth. And detected some pulsars, a bunch of quasars, etc. Okay, we're making our way through the different digressions. Now I'm going to have to tell you about like an astrophysical source that amazingly was only discovered a little bit more than a decade ago, which is called a fast radio burst. These are bright millisecond bursts of radiation. We think they come from magnetars, which are magnetized neutron stars. The reason we think this is we saw about 5 years ago one of these come from a very weak one of these, but like what looked a lot like a fast radio burst coming from a magnetar in our galaxy. About 5,000 we think are known with the CHIME instrument. They've only published 500 of them. They've also published 50 that are repeating. They likely have found many more repeating than this we just don't know yet. The ones that are repeating tend to repeat on of order 10-hour timescales. The repeaters are the most interesting for us because we're going to take our dishes and we're going to point at them, and we're going to know that eventually it's going to repeat. And it turns out that, especially for the repeaters, we're able to measure their distances, and their distances are perfect for measuring the expansion of the universe. The ones that we measure tend to be between 100 and 1,000 megaparsecs. Okay. So what does it take to detect these fast radio bursts? Well, we're going to envision two setups. One setup, we're going to have some dish in the outer solar system that and a big dish on Earth. This is the 80-meter GBT telescope in West Virginia. The signal to noise that you can detect at FRB goes as the geometric mean of the signal to noise on both of these instruments. This, of course, is going to be more sensitive, but you're probably not going to have GBT 100% of the time staring at your FRB. The other setup, you'll just have to wait. You'll only have dishes that are in space, but they can stare a lot longer. And so you're only sensitive to brighter FRBs. So we actually spent a lot of time this summer trying to answer this question, like how many would you detect? There's a fair amount of uncertainty here. I'm not going to go into the really ugly plot that appears below, but we tend to find that you tend to get more FRBs with 10% of the time here than 90% here. But we're finding that of order 10 to 100 a year is what you might expect. Okay, but I'm also going to show you in a little bit that 1 is really interesting. If you detect 1, you might be able to destroy this H-naught tension. Okay, we're almost through digressions. Outer solar system probes. We haven't sent that many things to the outer solar system. And unfortunately, it takes a while to send things to the outer solar system. So our record holder is the New Horizons probe, which took 10 years to reach Pluto at 34 AU. Part of the reason it took 10 years is it was 500 kilograms, which is pretty light. So the lighter something is, the quicker you can get it out there, of course. It turns out with this coming generation of rockets, you could get New Horizons out there in half the time, or you could get a heavier rocket, twice New Horizons mass in 4 times New Horizons mass in 10 years. The object that we've sent out the furthest is Voyager 1. It's currently 165 AU, and we're still communicating with it. And of course, anything in the outer solar system needs a pretty large radio dish. It had a 4-meter radio dish. At the end, I can show you movies of what getting spacecraft to the outer solar system might look like. But that's kind of fun. But if you request. Okay, so if you're sending things to the outer solar system, your internet, your data rates are not the most amazing, and so a worry is I'm detecting these FRBs. Can I actually even send the data back? Again, we're going to just reference New Horizons. It had a 2-meter dish, and it was able to send back from 40 AU data at 1 to 4 kilobits per second. Of course, we're going to have a bigger dish, so we probably can do better than that. But it turns out the really nice thing about FRBs is they're short. So an FRB it lasts a millisecond, and you need to sample the voltage at a gigahertz. And so you only need to send about 4 million bits back. And so if you send that over an hour, it's actually 1 kilobit per second. So like the data rates are achievable because these FRBs don't last very long. Okay, digression 5 and final digression, and not super serious, this one. I'm amazed. This is an actual photo. Like we're living in a weird world right now, for many reasons. But it's getting easier to launch things into outer space, and in fact, the cost for launch to launch a kilogram into space was $10,000 a kilogram for a long period of time, and now it's, if I extrapolate, now it's more. It might, in a few years, it might be more to send me from Seattle to Providence than to send me into space. But okay, more seriously, like what this means is the cost is mostly in developing your spacecraft. It's not to launch the spacecraft, and this is whether it goes into the low Earth orbit into the outer solar system. Okay, you guys made it through. Okay, now we're going back to measuring distances. So I motivated things in terms of parallax, but we're going to switch our way of conceptualizing distance, even though there's an equivalence. And we're going to talk about measuring the curvature of the wavefront. So I have this source, which is an FRB, and its light is going to travel to these 3 detectors, A, B, and C. Its light, its wavefront, of course, is curved. It is spherical. And so if I have 2 detectors, A and B, I cannot measure the direction to the source and the curvature of the wavefront at the same time, because I only have one time difference, the difference in arrival time between A and B. But if I have 3 detectors, I can solve for both. I can solve for both the angle of the source on the sky and the curvature of the wavefront. Of course, this is a 2D image. In 3D, I have 2 angles on the sky, so I need 4 detectors. So With 4 detectors, you can measure the angle of the source on the sky and the curvature of the wavefront. Of course, if you measure the curvature of the wavefront, that is a direct measurement of the distance, a geometric measurement of the distance, because for obvious reasons. Okay, so how big is this curvature of wavefront signal? So let's now consider 2 detectors. So this is a reference detector and a second detector. I can write an expression for the delay, how much earlier light arrives at the second detector relative to the first detector. There's a term that owes to the direction that the radiation is coming from, and there's a term that owes to the curvature, of course. We want to measure this curvature term. How big is it? So the curvature term is given by this, the distance between the detectors with some projection, divided by 2c, the distance to the source. And so if I evaluate, if my detectors are separated by 40 AU, and the distance of the source is my fiducial 200 megaparsecs, this is a 20 nanosecond effect. 20 nanoseconds, if I convert that to distance, the light travels is 6 meters. That's huge. Okay, so we want to detect this curvature. Okay, so how well can I time things? How well and measure this curvature term? Well, my fractional error on the curvature term is my error in timing divided by the size of the curvature term. This is also the fractional error that I measure distance. So and so I just plug things into my expressions, and if I evaluate the error that I can time my electromagnetic signal to be the inverse of the frequency, and we're going to motivate why this is a plausible assumption. In fact, it's a very conservative assumption. And I stick things in, so 40 AU, 200 megaparsecs, a frequency of 4 gigahertz. Then my error on the curvature term, which is my error on the distance, is a 2% fractional error. 2% is roughly our error on distances from all the supernova used for the H0 measurements. And so if I can, but this is with 1 FRB. So with 1 FRB, I can potentially achieve, if I had these specs, the same error that we have from all of the supernova. But this all relies on this assumption that I can time things to the inverse of the frequency. So how good of an assumption is this? Okay. So we've discussed one timing error, which is just how well I can align my wavefronts, like from VLBI timing, which goes as the inverse of the bandwidth. If I have a wide bandwidth, that's like the inverse of the frequency. But there are other timing effects that you might worry about. Like my electromagnetic radiation from this FRB is traveling through a cosmic plasma, and this will add delay. There also could be gravitational time delays. It turns out that there are 2 plasma effects that you have to worry about. And the first effect is called dispersion. This is the effect that if I have light that's traveling through the universe, it will, because the universe is not a perfect vacuum, it will not travel at exactly the speed of light. And it turns out that the lower the frequency that light is in a cosmic plasma, the longer it will take to arrive. This is actually how we discovered FRBs in the first place. So this is actually the first FRB ever discovered. It's before we actually even knew FRBs were a source. This is called the Lorimer burst. It was only 6 years after that we realized FRBs are a thing. This is 1.5 gigahertz, and this is 1.2 gigahertz. And this zoop that you see is the fact that the FRB has arrived earlier at 1.5 gigahertz relative to 1.2 gigahertz. And this is because the FRB has traveled through this cosmic plasma. For us, this effect manifests in that if I have one dish that's looking through the universe, it's going to go through a different set of electrons than another dish. And so that relative difference in dispersion is going to look like a delay that will confuse our measurements of distance. Fortunately, because of this frequency dependence, which is unique to this effect, you can take it out as long as you have a wide enough bandwidth so that you can see that it's changing with frequency. And actually, your phone uses this to great effect for GPS. Your phone wouldn't know its position to 20 meters because of dispersion at 1.5 gigahertz from the ionosphere. But GPS satellites use 2 frequencies, and it turns out that with 2 frequencies, you can eliminate this effect perfectly at the cost of somewhat larger errors. And so so for us, we need a wide bandwidth so we can fit this effect out. Okay, second plasma effect. This one is a little bit more worrisome, which is called scattering. What scattering is that the electrons in the interstellar medium of our galaxy, so the medium between stars in our galaxy, have a lot of inhomogeneity. And this makes it so that the wavefront of electromagnetic waves will progress faster in some regions where there are more electrons than in other regions where there are fewer electrons. And so it makes it so that certain regions are focused and some other regions are defocused. And so the light that arrives from a source will come from will follow different paths. So there will be multi-path propagation. And these different paths the light will take different amounts of time to travel along those paths, so they will arrive at different times, and this will smear out your signal. If you smear out your signal, this makes it so it's harder to time it from the FRB. And this is an example of this effect. This is a pulsar in our galaxy observed at really low frequencies, much lower frequencies than we're thinking about. And so you can see at 76 megahertz, its pulse is relatively narrow. But as you go down in frequency, it gets wider and wider, and it's because you have some of the light traveling paths that are the paths that the light is traveling are differing more and more from the straight line path. Okay, so it turns out that there's a way to avoid this. This effect is strongly frequency dependent, as you can see, and it's well understood from studying pulsars in our galaxy. And so we know from studying these pulsars that if you go above 3 gigahertz, this multipath propagation goes away. And so we're forced to observe at high frequencies above 3 gigahertz. Okay, final time delay to worry about is gravitational time delays. So your FRB light will travel across the universe, and sometimes it'll come near a star. And actually, as it goes through our galaxy, it'll likely come within about a light year of a star. And sometimes it will pass near another galaxy. And it will, if the FRB is 100 or 1,000 megaparsecs away, it'll likely come about a megaparsec from another galaxy. And so it turns out that the closer your light passes to a gravitational object, the more delayed it will be. This is called the Shapiro time delay. But this effect is small, but it gets large if your baselines get incredibly long. So you can see I've evaluated these at 100 AU. So this starts to become an effect that you would worry about once we're talking about a humongous system. It also has an interesting angular dependence that would allow you to remove it if you have enough measurements. Yeah?
Sorry, just trying to understand why it's like the square of this separation. Is it just because the two paths are very different sampling of an individual target?
Yeah, that's right. This is a differential effect. So you're right that if I were doing like a Shapiro time delay, it would be just the potential, which would be a GM over R. But now we have two paths, and so it's actually the next order of that, and so then you get so it becomes quadratic. Yeah. Good question. Other questions? Okay. So we have all of these different delays that we were worried about. We have dispersion from our galaxy. This is our estimate for that effect. That's removable because it has a frequency dependence. There are the curvature terms that we want to measure. So this is if it's at a source at 100 megaparsecs and 1,000 megaparsecs. We have these gravitational type delays that are small except at really long baselines. Scattering and this VLBI timing. And so what I'd like to emphasize is that other than the removable dispersion, the curvature effect is bigger than all of these others, which is good. So we can measure it. Okay. And maybe another thing to emphasize, scattering is going to limit our sensitivity often at lower frequencies. At high frequencies, it becomes a lot smaller. Okay, so this is kind of the money plot. So this, like taking all of these different sources of error, how well do we forecast you can measure distances to extragalactic objects? So far, we've been highlighting that we want to do this at 200 megaparsecs. Of course, you want to do this at many distances, especially if you're interested in dark energy. Let's take 200 megaparsecs, and let's say we have satellites that we've sent 25 AU in two directions. So I have a 50 AU baseline. Then with 50 AU baselines and 4 gigahertz, at 200 megaparsecs, our prediction is that you might be able to measure a distance that's a little bit larger than 1% to a single FRB. And this would resolve the Hubble tension. And actually at 8 gigahertz, because the scattering is setting our sensitivity, the sensitivity gets even crazy better. Okay. And the sensitivities, if we were like crazy ambitious and had 100 AU baselines, it becomes possible to measure the distances to objects on the other side of the universe. Yeah.
Your delta V curve without the particular velocity for a single object starts limiting.
Yeah, that's right. And so you can see that I chose a point where they're kind of equal. But yeah, you're right. If I was doing this at 100 megaparsec, I'd start worried about the fact that there are velocities in the universe. This is why we took 100 megaparsecs as we need to do better than that. Or this curve, which is the y-axis on these Hubble plots diagrams that we were seeing in the beginning. This curve becomes your limiting factor. Yeah.
With multiple targets, you won't end up averaging over the delta VG.
Yeah, you do. And so you potentially get a square root of n, except when they're really close, the velocity field in cosmology is very coherent. And so you don't exactly get a 1 over square root of n. It's because like an FRB that's 100 megaparsecs, so in that direction, their velocities actually are correlated. So it doesn't average down as fast as you would hope.
From a technical
Yeah. So I think we know a lot more about FRBs around at 4 gigahertz, or even most of our observations of FRBs are at 1.5 gigahertz. That's right. We have some detections of FRBs at 8 gigahertz, and there are a couple examples of FRBs that have a flat flux all the way to 8 gigahertz. Some of the young, really quickly repeating FRBs. But yeah, I think it's also the case that when I say it's limited by scattering, there's a lot of, it's quite possible that there's some sight lines through the Milky Way that are unscattered, that we're being conservative because we're taking the mean scattering, and we're not even assuming perpendicular to the disk. We're actually assuming kind of some 45-degree angle through the relative to perpendicular. So it's even for 4 gigahertz. I think it's possible you can do better. But yeah, 8 gigahertz, there's more uncertainty in the properties of FRBs. Okay, so that's the idea that you need. So you would have you need 4 dishes in the outer solar system. Ideally, you would need ground-based support to at least to ping the dishes to act as like a reference clock. The dishes also need to have clocks atomic clocks that are comparable to the atomic clocks on GPS satellites. On the ground, ideally, you also would have a really big dish, like a 100-meter dish or 80-meter dish that is able to get a template electric field that you can use to pull out the signal from the satellites. The satellite positions need to be known very well, which gets back to like something that I mentioned when we were talking about GPS. So the satellites will have to point to each other and measure their separations. And this needs to be done of order every week. And so they'll calibrate the array geometry. We need to know the geometry very well. Then they'll look at FRBs. They'll stare at these repeating FRBs. When a FRB goes off, they'll save the data. They'll send it back to Earth. And then maybe you'll look at another FRB and keep going, calibrate the array geometry, again, and so on. Questions?
What's the interval of repeating for these sources?
Yeah, that's a really good question. We only have 50 so far that have been reported. Some repeat on hour timescales. Many of them repeat so for the ones where we know they repeat, we've only observed them for 9 days because most of the repeaters were discovered by this CHIME telescope, and so its time on the sky was 9 days for high galactic latitudes. So within 9 days, we know that these 50 repeat, and some of them repeat on hour timescales. Yes.
I'm a little confused by the template part. You're still going to only send when they trigger on something?
Yeah.
And is the idea that the template helps you rather better than cross correlation and figuring out the time delay?
Yeah, this is really good question. So the question is how does the template help? So there's like two things that you can imagine happening. One is that the satellite itself can trigger. And if the satellite can self-trigger, then it would just have to store that 1 millisecond and send it back. It's also possible, and then you would use the template to correlate. It's also possible that the satellite will not have the signal to noise to trigger. The light travel times to these satellites could be hours. If they're at tens of AU. So then, if you have terabytes of storage, and it turns out you would need of order like 10 terabytes of storage, then you could store a couple hours of the electromagnetic voltage. And so then when your big dish on Earth detects the FRB, it could then quickly, you would relay that an FRB has gone off at some time, and it would store it wouldn't delete the 2 hours it's been saving, and then you would send it back. But that mode then requires that you have a lot of storage on your spacecraft. Okay. Any other questions about measuring distances? Because we're going in a different direction, like other things that these spacecraft might be able to do. Okay. Okay, so we've been trying to build up the science case for this. Like, just having dishes in the outer solar system, they must be able to do other science and not just cosmic expansion. And so these are our ideas, and I bet there are other ideas for what this system could do. And so one idea involves the dark matter. And so if I have this FRB going off, this is a repeating FRB, and I have two dishes. And the dark matter in the universe is very clumpy. And there are some models where the dark matter is even clumpier than in a vanilla WIMP model. And in fact, even a relatively motivated model, the QCD axion, can be clumpier than the WIMP. And so these dark matter clumps, it turns out because of the magnitude of velocities in the universe, they move about 100 AU in a year. And so there's a wind of these dark matter clumps that are flowing between us and the fast radio burst. And remember, we have these gravitational time delays. Like if a sight line comes close to a dark matter clump, its light will be more delayed than if it doesn't. And so what will this look like? Well, it will look like the FRB jiggling around. Like, so this wind of dark matter will impart these time delays that move the FRB around. And so if you watch a repeating FRB long enough, you can try to constrain the structure of dark matter on tens of AU scales. And this is our forecast for how well this would work. So this is the nonlinear matter power spectrum of the universe, the y-axis, which quantifies the size of matter fluctuations in the universe. And this is wave vector. The highlighted regions in blue are where we have constraints. So we've constrained this power spectrum to be to exquisite precision at wave numbers less than 1 or 10. But on really small scales, we don't have very good constraints. And so the blue here is if you take fits to the nonlinear matter power spectrum that are calibrated to about k of 100, and then you very irresponsibly extrapolate with a power law. But in this paper, we come up with more motivated models. I mentioned this QCD axion model that has these axion mini clusters, and we also have an early matter domination model where in certain models it's motivated that there's some excess power at some excess fluctuations at these really high wave numbers. And then this is what we think could be constrained by the system. So potentially this is the best way of constraining the clumpiness of dark matter on really small scales. And then and this has been a project I put a lot of time into in the last 5 months. But we also think that this potentially could be interesting for gravitational waves. And so just to fill you in, and you can kind of see very quickly, in about 10 years we plan to put LISA in space. And the LISA sensitivity is shown here. And where the solid ends is where it's spec'd to go to. It's mostly off the plot. But LISA loses sensitivity around 10 to the minus 4 hertz to gravitational waves. We also have a detection of gravitational waves at 10 nanohertz, so 10 to the minus 8 on this plot, with pulsar timing arrays. The reason LISA loses sensitivity is we can't correct for accelerations on the LISA spacecraft sufficiently at low frequencies. And so the sensitivity of LISA is set by how well we can constrain, isolate it from accelerations. And the people talk about the microhertz gravitational wave frontier as a frontier where we don't have good ways of constraining gravitational waves because we don't have the technology for the acceleration control that would enable us to do a LISA-like mission. So the idea here is, okay, if we float these dishes in the outer solar system, all of the accelerations on the spacecraft are down humongously. So if I'm at 30 AU, the major sources of acceleration are the solar wind and solar radiation variations. If I'm at 30 AU, they're down by a factor of 1,000 relative to 1 AU. It also turns out that at low frequencies, the gravitational wave signals are way larger. So these are the signals that you expect for merging supermassive black holes in the universe, which is also a reason why you would want to target this band. Like these really interesting sources fall at these low frequencies. And so these are forecasts for how well you might be able to do. The blue is if you just have a GPS-like atomic clock on your spacecraft. The magenta is if you have 100 times better than the atomic clocks we put on GPS satellites. And the purple is, it turns out that you are able to eliminate your clock noise if you do interferometry. The way you do interferometry is you have 2 dishes on one spacecraft and that are broadcasting to single dish spacecrafts, because then you can send your signal back and then interfere it. And that eliminates clock noise. And then you get to this really interesting sensitivity. Yeah, this is a prediction for the stochastic gravitational wave background. Once you reach the stochastic gravitational wave background, there's no reason to make your instrument much more sensitive, because that's going to set your noise. And so you can see that these predictions are potentially starting to hit this background. Okay, so that's the end of this talk. So I don't know. The future. There's a lot of time in the future, and I think we have the technology to execute this. It wouldn't be cheap, but essentially it's like putting GPS satellites with big radio dishes, but not that big in the outer solar system. We would need 4. You'd want them essentially to be at least out to Pluto. You would really eject them from the solar system, because once you get them that far, you just want them to drift out. And the further they drift apart, the more sensitive you are. The sensitivity scales quadratically with this separation. And potentially there's other interesting science too. I'm even not convinced that this isn't a gravitational wave science mission that also can do the expansion of the universe. All right, thank you.
Doesn't take up too much time. Of course, it's the hardest place to get the mic to that has the first question. Passing that down.
A couple of slides back,
Yeah.
or like halfway through the lecture, you mentioned doing ground-based telescopes with a space telescope as well.
Yeah.
And the reason it would not work is because the GBT time would be too much, but why does it have to be the GBT? Could it not be any other radio telescope? It's not a...
Oh, yeah, that's right. I mean, maybe we could coordinate. And in fact, there's a 500-meter dish in China called FAST.
Mm-hmm.
Like, that would be the best. I think you could motivate this with having a much more complete fraction of the time covered by big things on Earth. It's a matter of motivate. Of course, you'd be taking these telescopes away from the radio astronomy community, and so I don't know if it's feasible, especially to propose a mission that also requires a lot of ground-based support. And so it's also nice that you are able to detect some of these the brightest FRBs that go off with just the system itself.
Mm-hmm. But it doesn't need to be a large dish, because the dishes that you're sending to space would also be...
Oh yeah, but then if it's the same size as these, then you're not gaining from it. But yeah, if it's even a 30-meter dish could be interesting. Yeah.
The question.
Can you comment on what's really known about the FRB sources a little more?
Sure.
Do you think they're magnetars, or all magnetars the same? And how many unique measures to beat the current data?
Yeah, well, I think potentially for the Hubble, because it's only one parameter, as long as it's far enough away so that you don't have the velocity error being important, then you potentially only need one for the Hubble tension. And then for dark energy, you want ones that are further away. And so really, the longer the baseline you have, the more sensitive you are to the distant ones. But this is a good question. We're actually trying to do these type of forecasts now for if we had 100 of these, what could we say about Hubble and dark energy? But I think at some level, it's just one can nail Hubble if you have the sensitivity that I'm claiming. And then you asked about magnetars. Actually, FRBs is such an interesting field because it's so new, and so we tend to learn something every couple, or several things every year. So we know that there's a really dim FRB from our galaxy that was a magnetar. We also have a ton of other phenomenology about these FRBs. Like some are repeating, but most are not repeating. And there are other dichotomies. And so it's not impossible that there's a difference. There are multiple sources that create FRBs. But I think the simplest assumption is that it's these magnetars because we have this example in our galaxy. And even there's a lot of evidence that probably they are neutron star related because a millisecond is kind of a neutron star type of time scale. They're coherent emission, which in some cases we even see repetitions that look like neutron stars, star physics. And so there is a lot of evidence that they're probably associated with neutron stars.
Nice talk. I was checking my phone probably when you were saying this, but in terms of the spectral information, you get higher resolution. Yeah, what gain do you get from this configuration in terms of getting better spectra of the FRB?
Yeah, I guess you're never going to have a better spectrum than on the ground, just because you have much higher signal noise. I don't think there's any gains from that. It's just from you have much higher angular resolution because of the baselines.
And then part of my ignorance, any information about polarization, or is it noisy?
Yeah, it turns out that FRBs are highly polarized. That's right. There's tons of papers on the interesting phenomenology of the FRB polarizations. For this science, that's not super relevant.
So Matt, you talked a lot about the wavefront curvature time delay.
Yeah.
Have you looked at what the positional accuracy and whether there's something interesting there? I'm thinking particularly of, can you use the peculiar velocities to your advantage in the sense that these things should drift a little bit in position? And now if you have a 100 AU baseline, you could start actually seeing, for example, the relative motion of the Milky Way and the galaxy over the course of 10 years.
Yeah, no, this is a really interesting question. I think at 100 AU, the drift from the large-scale peculiar motions in the universe, at 100 megaparsecs, the drift from large-scale peculiar motions is about a microarcsecond, and here we're talking about 10 to the 4 microarcsecond angular resolution. So you would you'd measure for the tens of galaxies where you detect FRBs, you would measure their peculiar velocity very well. Yeah, you get the transverse component. And even if you were able to, the line of sight component, like it's also, I guess there's also the question of whether the FRB is exactly moving in the same way as the galaxy. Yeah.
So apart from all other interesting science you could do with this system, as far as the Hubble tension is concerned, if you were to launch the satellites today, it would probably take 7-8 years to get to 30 astronomical units. So do you think that Hubble tension won't be resolved by other means in this?
Yeah, so this is a really good question. Is it even worth motivating this for the Hubble tension? So maybe another cell. I don't know. This tension has been around a long time. I feel like with supernova, this is not going to be resolved just because but that's my feeling. It might be that these gravitational wave sources in 15 years when we have the next generation Einstein telescope and the U.S. version that we will get at these neutron star mergers and we're convinced enough that it's resolved. I think another argument for this might just be like measuring the Hubble constant so well that it's no longer a parameter that where its error is so much smaller than other cosmological parameters, so that we can start constraining these other things like the expansion history better. And so you could imagine having like, if I have, but maybe if you get FRBs at sufficient distances, maybe even a few parts in 1,000 measurement of the Hubble constant, and then I think this is going to make it so that you're better able to constrain the properties of the dark energy because you have this like redshift 0 point fixed. But I think this is a really interesting.